Today is our first stats class. As I put in the message, we're going to start off a bit slow. The reason being we're moving away from, I guess, the abstract language of Python into the application of the abstract language of Python. And I think for some people there's growing pains around that, and that's fine. So the functions that we're going to write today are going to be simple functions related to stats that probably everybody in this space is familiar with. Stats related to centrality. Average, right? That's one of the ones we're going to think about. We're going to think about median. And we're going to take those concepts and, write simple code to implement those kinds of functions. So that said, I'm going to share my screen. I'm also going to take a quick aside. I just realized that there's something I want to point out to everyone. And I'm going to need a web browser to do that. So, 1 second. So, we work out of this course outline. That's our place of truth. And I'm assuming most of you go here, right? To figure out, the next things we're going to look at, right? The slide decks and also suggestions for homework, right? The way that we think about homework is that it's going to be at your pace. Different people are going to complete this in different spans of time. There are going to be people who don't need to do all the homework, and there are going to be people who need to review things multiple times. Seeing as this cohort, the last day of this cohort, is going to fall in very close proximity to the interview deadline, the cutoff for the technical interview. So with that in mind, if you are aiming for the August cohort, it might be well worth your while to study ahead. And I want to give you some suggestions in that regard. Where to put focus. So once your Python, let's say your core Python is together, basically you have a good understanding of list and dictionary manipulation. That's, I think, indicative of your Python being at a place where if you have the other sort of analytic approach that we teach, you can pass the technical interview. As we've said, you've probably heard us say this a lot of times, we don't need you to be the best programmer, but we do need you to be able to apply, the core of Python. The materials that I'm going to point at here, the days that I'm going to point at, are specifically related to the technical interview. And I'm going to put this in Slack. I think it's probably helpful for everybody to see it in a single place. I'm going to put it in this thread, so I'm going to say, slide decks directly related to the TI, and I'm going to leave this for y'all to work ahead if you are aiming for this August cohort, which I think many of you are. So there's this idea of a general analytic approach that we're going to talk about when we get there. There are discrete random variables. The technical interview is going to be concerned with discrete and or continuous distributions. There are Bernoulli trials and binomial distribution. Those are very important. We would expect you to be reasonably familiar with those and be able to do textbook problems. There's the Poisson distribution, same thing. We would expect you to be able to implement in Python some of the formulas around the Poisson distribution. In any of these cases, we don't expect you to have any formulas memorized, just to be very clear. I always get asked this, about 10 times around, and I'll keep saying it. You don't need to memorize formulas. Don't worry about that. I am also a proponent of memorizing things, especially those kinds of formulas, because they appear in other places. But that's not something you need to do, and that might just be me being a weirdo. So this continuous distributions lecture is going to be important. We're currently not testing anybody on the geometric distribution, but we would expect you to be able to recognize it. Same with exponential. Geometric is a discrete distribution, by the way. Exponential is a continuous distribution. Those are covered in slide decks. If you want to work through a slide deck on the geometric distribution, there is this, well, I'll just do this. There is this directory under slides, DS Premium Prep slides, that has, that has some extra stuff that we don't currently instruct on, but there is a geometric distribution slide deck in here that we might cover somewhat when we get there. We might skip it. We're probably going to skip it, just to be transparent. And then beyond continuous distributions, we don't need you to know conditional probability or Bayes theorem for the technical interview, although it is very important. We're not currently testing on that. There is this slide deck called Technical Interview Review, and what this is it is a stack of problems that look sort of like what you might do on the technical interview. Incorporates this idea of a general analytic approach, which we're not going to talk about today, but we'll talk about soon. And it's just a battery of problems. So let's just take a look at this. With all of, there's a little bit about the technical interview, and then it is just a stack of breakouts with solutions. If you're thinking about it this way, and if you're if you have this kind of mentality in the world, you could make a set of digital flashcards, right? You could just screen capture all of these, throw them into Anki if you're familiar with Anki or some other digital flashcard system, and you could have one side be the breakout, the other side be the solution, and that wouldn't be, in my opinion, wouldn't be the worst way to sort of, narrow in your study for the technical interview specifically. Although, if you're looking at these solutions, some of these are going to be inaccessible to you if your Python isn't at, the appropriate level to be able to do them. So, a lot of things are contingent on Python, which you are likely aware of. Okay. So, if you have any questions about that kind of stuff, DM me on Slack, and I'll do my best to get back to you. Just fair warning, my turnaround time on Slack messages right now is about a day. Usually it's more prompt, but I'm also on a development project, so I just want to be very clear about that. If you don't hear back from me right away, that's likely because I am off Slack working on some development. Okay, so I'll just put that list of stuff in the Slack. Those are all the slide decks that are directly relevant to the technical interview. Feel free to copy that somewhere, save it somewhere, DM it to yourself, right, so you can look at it later. The other thing that I want to point out is there is a Chrome extension if you want to be able to view MathJax, or the math equations, which are written in a form of LaTeX, which is essentially a formatting language, where you can write math, right? If you're wondering how math is written, behind the scenes, how do you get all the symbols and everything, that's usually LaTeX. There's an implementation of LaTeX called MathJax, and if you want to see that rendered in GitHub, which I'm assuming you do if you're looking through the slides there's a Chrome extension that, it's very lightweight. You can just install that, and it'll render all of your MathJax that comes up in GitHub. So I just put that in as well into the Slack. I recommend you look at it. Sometimes, well, I'll just leave it there. I recommend you install that extension if you're going to be looking at the slide decks on GitHub. Okay, so that is the preamble, and let's kind of get into what we're going to talk about today. So pretty much any stats course is going to start somewhere, and if you're starting with a very probability-based course, maybe you start with simple probability problems. We're going to start with simple metrics, and we're going to put that on for today on measures of centrality. In the midst of that, we're going to talk about the why of statistics. Why are we thinking about statistics in the data science space? We're going to go over 3 measures of centrality, kind of the basics. Probably most of you know what these are. We're mostly focusing on writing Python to implement these. We're going to talk a bit about sampling, and if we have time, I'm going to demonstrate, this is kind of a seed for the future. Sampling is going to become really important as we go forward, and then just more abstractly, we're going to talk about continuous and discrete data. Okay, so the why of probability in statistics. Very generally, there's a truth about data science that not everyone realizes. Data science is new. It's a new field, and it is moving very fast, and it's changing very quickly. That's, I think some people come to the space because they're like, it's a green field. Well, it's not exactly a green field. It is a rebranding and a deepening and a broadening of a few different fields, right? So at the core of data science, the first data scientists, if we're thinking about them, they were statisticians who then were being called data scientists. And that's kind of how that happened, right? That's, mid 2000s is what we're thinking there. I think really that hooked in like 2010, 2011. And from that moment, the idea of data science scattered into a bunch of subfields, all called data science, right? So if you are into natural language processing or computational linguistics, you're a data scientist. You kind of got subsumed by that moniker, whereas the specialization that you might be in is very related to text manipulation, and you may not be as familiar with things like digital image processing, which also was absorbed by data science, right? So we're sort of in the phase of time where being a data scientist means a whole bunch of different things, and also the subfields are re-emerging from that space, right? So you're like, I'm a data scientist with a specialization in this. Like, this is where my set of ability is, right? It might be, for some people, some data scientists, it ends up being digital storytelling. For some data scientists, they may be doing the exact work of a statistician of 20 years ago. And, how could that be? Well, it turns out that if you look at the seminal works in machine learning, namely Introduction to Statistical Learning, which is a book that we tend to recommend. It's linked from the Galvanize repo, from the open source repo that for our course today. That book is written by people who are statisticians, who other people call data scientists, and if you watch their lecture videos, they just tell a bunch of dad jokes about that kind of thing. We used to be uncool, and then we became cool because everyone started calling us this. And I think that's part of the part of the reality. I think the other part of the reality is that once there was the emergence of data science, we have an influx of other fields that heavily alter it. Everything from sort of fundamental distributed computing technologies that come up, right? If you're a low-level systems engineer, you're developing things that can be highly parallelized, which, maybe that's really great for gamers over here. It also created the ability to have massive neural nets with tons of hidden layers. The other thing you have is a heavy influence of computer science, right? Computer scientists have contributed many of the models that we see in data science. And those are different very different fields. Statisticians and computer scientists are coming from pretty different backgrounds academically, but there is a convergence in data science, and data science as a field is kind of the abstraction, in a sense, of a lot of these sciences, including social sciences, right? Some of the most forward things that we see in data science, some of those things are from the social sciences, some of the most innovative models, right? If you're familiar with the Gottman method, there are linear models, which is a couples therapy approach. There are linear models developed by the researchers in the Gottman method that, in terms of predicting relationship outcomes and things like that. And those models are machine learning models at the end of the day, right? So we're pulling in from a lot of different spaces. Obviously, genetics, mapping the genome was, the human genome was a huge boon to the data science space. A lot of those models are very, very relevant. And in stats in general, right, the models that, in data science in general, a lot of the models come directly from stats. Like you can go to even intro stats books, and you're going to see linear and logistic regression, sampling methods, of course, things related to confidence intervals, expectation, variance, and things like that. So there are these different ways. I think one of the things I'm getting at is that there are different ways that we think about the field and talk about the field. There's this joke here. When you're fundraising, it's AI, right? If you're out in the world, you're like, oh, learn AI, right? What does that even mean? When you're hiring, it's ML, right? Machine learning. When you're implementing, it's logistic regression. I think this is, this comic's a little bit old, but, people hire, when people are hiring, they don't necessarily know what they're hiring for. They know what they want to have happen, unless you're getting hired by a data science team, which is often the case, actually. But if you're getting hired, if you're getting headhunted, that person doesn't actually know what you do in a lot of ways. They're not really clear on it. They just know that somebody wants to hire you, and so the way you talk about yourself starts becoming really important. When you get down to it, it's about implementing machine learning models and essentially digital storytelling and the ability to leverage critical thought. Okay, so let's think about basic summary stats. We're going to cover a little bit more than what's on here, not today, but in terms of our summary stats, which central tendency is in that area of summary stats. We're going to cover mean, median, mode. And in terms of variance, which we're going to do next time, we're going to talk variance, standard deviation. We're also going to talk IQR. I think that's a very helpful thing. Outlier removal. When we get there, we'll see that. Okay. So we're going to start at the most basic of the basics, right? We're going to talk about the mean, or the average, right? So the mean is very simple. And, sorry, I have a sketch program open, just important. Okay, so the mean is very simple. It is the sum of the numeric elements divided by the count of the numeric elements. That's all it is. And what does that look like mathematically? Well, it is the sum from, we can say, I is 1 up into n, okay, of all the elements in a numeric list, divided by the number of elements, okay? Oh, I don't know why that happened. There we go. Okay, so what is A? This should be A sub I, by the way. So what is A? A is going to be, for our purposes, a list of numbers. So A could be, let's do something really simple, 1, 2, 3, 4, and 5. So if we add these up and divide by 5, what do we get? We get, what is that? That's 15. We're going to get 3. And I think 3 is obvious. Like, this is central. And for the mean, this is central in more than one way. There are other there are other measures of centrality, but in this case, we're adding everything up and dividing by the number of items. And this gives us one type of centrality, known as the mean. So we can do certain things to the mean to kind of narrow our space or remove potential outliers, right? What if this was 1, 2, 3, 4, 5, and then 5,000, right? Like if it was that, 1, 2, 3, 4, 5, 5,000, that would that would put our mean at 5,015 divided by 5, right? That doesn't seem very central or representative of our data at that point. It might be. We can't say for sure that it's not, but we can kind of say it looks like our mean is dragged way to the right, right? Because what would that be? That would be 1,003. 1,003 is, well above 4. So if we wanted to kind of rectify that a little bit, we might, for example, trim out this element and this element. And that's going to give us something called the trimmed mean. Okay? The trimmed mean. And so I'm just pointing that out. I'm going to have you write a mean function in just a second. And one of the optional parameter that you can put into that function is a trim parameter. Okay, so if you trim in this way, you're taking off the top and the bottom one element or two elements or three elements, right? Whatever that is. An advantage of this is you might be able to further centralize your mean, right? Because if we trim this out, then that's going to be what is that? That's 5, 9. That's 14 divided by 4, which is closer to 3, right? That's not the worst. It's a little bit more than 3, and maybe that's more representative. But a disadvantage of this is that we're removing data, and you always want to be careful and thoughtful about removing data. There might be a phenomenon that we're looking at here where a 5,000 is going to pop up, within 6 samples, but maybe that 5,000 is actually representative of the data that we have at hand. Okay, so I'm going to have you write a mean function, and let me just snag this breakout and put it in front of everyone. You have the option of including a trim parameter, okay? That removes the greatest and least n values. So I'll leave that to you to figure out. And I will set a timer for 4 minutes. Oops. All right. Feel free to post your solution when we get down to the minute mark. Okay, so when you see, it'll say in my terminal 1 minute remaining or something like that. If you can hold off on posting until then, that'd be great. All right, so timer, I'm gonna set this for 5. Go ahead and, well, no, I'll do 4 for the mean. Go ahead and code the mean function and include a trim parameter if you feel up to doing that. If you have a solution, feel free to post it. So whatever you have so far, please post it in the Slack. And that's current. That's how we'll generally do this. Even if it's incomplete, even if it's not working yet, go ahead and post what you have. Okay, so we're going to code out this mean function, and we'll start this. We'll do the simple form of this, which is just we're going to pass in a list. And then we're going to return the sum of that list, right? That's that summation. We're just going to sum it. And we're going to divide that by the length of the list. So let's make some data. We'll call this A, and we'll just do that same one. So 1, 2, 3, 4, 5. And we can print the mean of A. Okay. So this is the simple form of this. And if I run that, we get 3. Something to notice, because we're dividing, this 3 is going to be a float. That's fine for our purpose. The mean of a set of data does not have to be an actual value in the data, right? It's a measurement, so we want to think about that way. And now let's put 5,000 in here, okay? And let's see what our mean is. That is not the mean that I thought it would be. That's really funny. So 835. I think what I said was really wrong because I divided by 5 when I summed it in my head and not by 6. So apologies for doing really bad math just a little bit ago when I said that. But at any rate, here's our mean if we throw 5,000 in there. 835 is way above any of these other values. So this might be a good case for putting in a trim parameter, okay? And I'm going to call this trim, and we'll trim it by 0 by default. And we can start working with this. So trim is 0, and this is going to necessitate rewriting this a little bit because I don't want to modify the actual thing that I pass in. I don't want to modify the parameter. So I'm going to make a copy of the list. And that's not to say that it's never okay to modify the thing passed in. It's just there's behavior there that is a little less predictable, and in Python it's generally not the best practice. So I make a copy of the list, and then I can say if trim by, or if trim is greater than 0, then we can, well, we have to do a couple things here. We need to get rid of the first and last, the smallest and largest numeric elements in it. How do we do that? Well, what we can do, well, we need to know what is smallest and we need to know what is largest. So we can sort this list, right? We can sort it, and then the 0th element is going to be, right, the smallest number, or the smallest value in there. And the last value, which is the sort of -1 value, is going to be the largest number, right? So in indexing this is very simple. We can actually say we're going to slice this from trim up into, whatever trim is from the back. So if this is 1, we're going to go 1 in from the back, so negative trim. All right. So if we do that, and then we set trim to 1, right? Then we should see the average, the mean of 2, 3, 4, 5. And that didn't work. Why did that not work? If trim is greater than 0. Oh, because I'm returning the list. I need to actually do list underscore here because I made a copy. There we go. Okay, 3.5. And, you know, I think we could argue that that is a little bit more representative if we're thinking about 5,000 as being anomalous in some way. Okay, so I'll just take that. I'll throw that in the Slack for anybody who doesn't have it. We're probably going to, well, we're going to be able to call back to the mean function at various times. Mean is utilized in a number of different places. That said, you know, we can always do the sum of the numeric elements divided by the number of, you know, the count of numeric elements if we need to construct the mean, and in that way we can avoid having a dependent function if we want. But, you know, dependent functions, especially small ones, are totally fine. And I think there are a lot of times where it's very helpful to write, well, a helper function, for that matter, where you atomize your ideas. But we'll see that in other places a little bit more. Okay, so let's utilize our function. I've got a story problem here that I am going to put up here. Feel free to start reading through that. I'll read through it briefly. I'm also going to share these lists of data. So give me 1 second. I will throw those in the Slack. Okay, so there's a journal article published in Indoor Air where we consider two different sets of samples, air samples, for urban samples and farmhouse samples, or rural samples, I'm assuming. So you're going to give the mean for each group, so the mean of urban, the mean of farmhouse, and then you're going to give the trimmed mean for urban and the trimmed mean for farmhouse. If you know how to do this, I want you to make a nice looking message using an F string for your print statements. If you don't know how to do that, I'm going to show you. It's the kind of thing that once you get the hang of it, it's really easy, and you know, makes your code look a little bit nicer, or sorry, your output look a little bit nicer. Okay, so let's do 4 minutes on this, and yeah, when we get down to 1 minute, feel free to paste in your code. Don't just answer these questions. Don't just put a number. Put in the actual code, right? So, you know, if you're calling out to another function in your file, copy all of that, and also put in the response to the solution that gave. So I'll set 4 minutes and go for that. All right, let's go through a solution for this. So here's our data, right? Urban and farmhouse. And the first thing that we want to do is we want to determine the sample mean for each group. And we've got a function to do that, right? That's the mean of urban, the mean of farmhouse. So that's easy, that's nice. What we can do also is we can round these values, okay? And maybe what I'll do here is round to 1 decimal place because that looks like a representative of our measurements. Okay, excuse me. So let's do that. And I mentioned, you know, if you know how to do this, wrap this in an F string. What does that look like? Well, we can put curly braces around this, and then we put it in a string, and y is, oh, I see what's happening. There we go. Okay. So let me do that again. Okay. And then we can just, you know, I'll print these, and then I'll make a better, you know, slightly cleaner message. So what I could say here is this is the mean, not rample, but sample mean for urban. And I'll just take that same message and say this is the sample mean for farmhouse. Okay. So that should give us a nice message here. Sample mean for urban is 21.5. Sample mean for farmhouse is 8.6. If you got something different from that, let me know. Okay, so the second part is determine the trimmed mean for each group. And what might be nice here is thinking about why the trimmed mean might be a good idea. So let's also print a sorted version of urban, and I'll print an extra space here, and we'll print a sorted version of farmhouse. And just look at this briefly to establish, you know, why might we do this. So for urban, look at where 21.5 lands. It's a little bit to the right in our list of values. Why is that? It's getting pulled to the right by these higher values, 80 and 35 being the higher of them, right? Or 33, 35, and 80. Whereas the rest of these, you know, if we're thinking about this, you know, kind of critically, there's a chance that 80 is an outlier, like an especially, maybe it's in very close proximity to, like, a factory that's, you know, I don't know, poisoning the air in some way, like a metal refinery kind of thing. Maybe that's happening in that neighborhood. So that might give some reasoning for, if we're trying to speak generally about the conditions, the air conditions in urban, we might want to say, okay, well, let's drop this 80, and if we do that, let's drop the 4 as well. Whereas if we look at farmhouse, that 8.6, just, you know, visually, kind of looks like it sits right in the middle of everything, right? Like we have kind of this even spread of values here. Yeah, so I think we can get a sense of that. Now, what I'll do, I'm just going to copy all of this, and so I can just add, oh, don't want to do that. Okay, so we can say this is the trimmed mean for urban, this is the trimmed mean for farmhouse, and then we just want to, you know, say trim by 1. I think, you know, we could trim by 2 actually for urban. I think that would be also reasonable. And even though we don't need to, and this isn't going to alter it very much, we'll trim also the what we're seeing for farmhouse. Okay. So our trimmed mean for urban, our sample mean, after it's trimmed, goes down to 17. I think that looks a little more representative. Well, I don't want to say representative because we don't know that 80 is an uncommon occurrence given our number of samples. Maybe it's important to include it, right? Maybe we don't want to fool ourselves into thinking that the air quality is better than it is in across these samples. But I think we can safely say that 17 appears more central. That doesn't necessarily mean it's more representative, but it does look more central. Whereas, and 8.2 for farmhouse is not really that different from 8.6, right? Like that's not, it's barely a significant difference given that we're dropping 21 and 0.3. So I'll paste all of this in. I think getting into the habit of writing good print statements that are meaningful, the sooner you get into that habit, the better. There are going to be times where, there will be times where you really want to see some kind of interpretable output. You got something different. Do you want to, here, let me look at your code and see what might be happening there. Yeah, that's interesting. So for farmhouse, yeah, I'm looking at this. So for farmhouse, the mean farmhouse is mean. Trimmed mean, trimmed by 1. What is going on there? Trim 0. Huh. Yeah, I'm not sure. I can't see offhand where that error is. If somebody else can take a look through that code and see if they notice something. Oh. Yeah, I'm not seeing it. I'm not sure why that would be different unless there was a difference in the actual data going in. But I think everything else looks sound. Interesting. Yeah, maybe it's a copy-paste error. I'm not seeing it offhand. Okay. So I think that's enough basis for understanding the mean. Let's think about a different measure of centrality. And I'm going to say this now. There isn't necessarily a better metric, right, between the mean and the median. I want you to think of these as being different things that you're measuring, okay? So when we're thinking about the median, we're not summing and then dividing by the number of items. What we're doing is we are choosing the middle value, right? So if we got 1, 2, 3, 4, and 5, a way that we can think about this is we're just going to, we're going to get rid of things on either end until we end up with something in the middle, right? And we can see if we do that, the median is 3. So what else? What happens? So this is an odd length list, so we very clearly have this thing in the middle that is our median. What happens if we have an even length list? It's going to be a little bit different. Just a little bit different, but procedurally, when you write code for this, it ends up being fairly different. And we want to account for the odd length list and an even length list. So how do we deal with an even length list? 4, 5, and 6. Okay? So we can do that same process. Well, it's just sort of an intuitive thing to do where we just cross things off on the ends until we have the thing in the middle. Well, we've got 2 things in the middle, right? 3 and 4. In this case, we actually take the mean of 3 and 4, which is going to be 3.5, or we just add them and divide them by 2, either way, right? So this is how we think about the median. It's the middle value. Does that middle value have to exist in the data set? No, not necessarily. Here's definitely a case where we see that it doesn't, right? 3.5 is not in our list of numbers. Now, that makes it a little tricky to code, a little trickier to code, but not much. So you're going to want to check if the list is even or odd. You're going to want to sort the list. So we can say check it's even or odd if we're thinking about this in terms of steps, right? So you can do that with your list. You're going to then sort the list. Well, you could do that in either order. You could sort first if you wanted. So sort our list. And then, you know, if it's odd, then you just return the central value. If it's even, well, I guess this is both part of 3. If it's even, you return the mean of the 2 central values. Okay. So it's fairly simple algorithm there. If we're thinking about this like here's a procedure, how would you do this procedurally using Python? It just looks kind of like that. So with that said, let's go ahead and code this. So I'm going to give you a version of that little algorithm I just wrote. Actually, this only has 2 steps, but you know it's kind of nice to have this in front of you if you need to reference it. So sort the list, find the middle value. If the list is odd, select the middle value. If the list is even, take the mean of the 2 middle values. I'm going to give you an odd list and an even list. Put that in the Slack. And I'll give you 6 minutes to code this. We'll go through a solution, and then we'll take a 5-minute break. So code the median function, and obviously make sure to account for even and odd length lists. So give me a thumbs up in the Slack if you want 2 more minutes on this. And otherwise, feel free to post your solutions. Okay, I'm gonna add 2 minutes to this. All right, let's go through a solution for this. I just want to be really clear, there are a number of different ways you could write this. I'm going to, in general, opt, at least initially, to write code that is easy to pick apart, easy to break down. And I'll do that in this case as well. So the first thing we're going to do with something we pass in, this list that we pass in, we're going to sort it, right? We're going to call sorted on the list, and I'm just going to call this the sorted list sorted. So that's where we start. And then we want to ask this question, is it odd? Is it even? We can check the length of the list mod 2. If that is equal to 1, right? If after we divide it by 2, if it's a length 7 list, we divide that by 2, there's a remainder of 1. That's going to work for checking odd if something has an odd length. So once I do that, I'm going to get the middle value, which is going to be the length of the list divided by 2. Now remember, if we divide, that's going to give us a float. So let me cast this to an integer, because we're going to use mid to index the list list sorted list. So return list sorted, and the index here is going to be mid. Okay, so that should work for an odd length list, and I'll wait to test this until after writing the next part. So what do we do if it's even? We can do something, I'll just say relatively similar, but remember we want to get two values out of this. So we want to get the upper middle and the lower middle value, right? I'm sort of doing that in the opposite order, but the lower and the upper middle value. The upper middle value, which I'll call upper mid here, is going to be that same, the length of the list divided by 2, right? If we have a length 8 list, we divide that by 2, that's going to be index 4, which is the 5th item in the list. We also want to get the 4th item in the list, which is going to be the upper mid minus 1. So we can get that upper mid just like that, and then we can take list sorted, and we're going to just add the upper mid with upper mid minus 1, right? And we're going to divide that by 2. So whatever the result of that is, we can just divide by 2. We could call the mean function on this. That would be fine as well, but it doesn't really matter. So, right, we're getting the value out of the list, the upper middle value, the lower middle value, adding those together, and then we're dividing that by 2. Note that we need parentheses here, right, because otherwise the division operation is going to go first. So we can just return the result of that. Okay. I'm going to grab those lists, and we'll just check it really quick. Make sure that this is doing what we'd expect it to do. Did I just call this median? I should have. Yeah, okay. So we'll take the median of the odd list and the median of the even list. So it looks like 14 and 12.5. There's a question, do we need to cast the even result to int? No. We don't need to do that. Because we're casting the index itself. We only need to cast the indices. We don't need to cast the actual measurement. So we don't need to cast any of this, as it turns out. We can just use it as is. Okay. So let's take, I'm going to paste this solution in, and then we will take a break. And I'll paste in the output too. So I'll set a 5-minute timer in just a moment. Feel free to start your break now. All right, let's continue forward. Oh, my apologies, I was muted. Let's go ahead and continue forward. So we're going to take a little, we're going to look basically at that last question again, okay, where we have urban and farmhouse. I'm not going to do this as a breakout. I'm just going to show you that we can answer we can answer the same question, and we can potentially make a comparison between the outputs, right? So again, we've got this article from Indoor Air. It's the same numbers, right, for urban and farmhouse levels of endotoxin concentrations. So we've got that here, urban and farmhouse, and what I will do is I'll just snag this code and repurpose it. And here we've got the median for urban and the median for farmhouse. And I don't need to round these, but it's not going to hurt anything to do so. So I will just leave that in so I don't have to delete a bunch of stuff. Let's look at, I'm going to uncomment our mean for both of these. So we should see we should be able to make some kind of comparison between the two. That's my purpose here for doing this. Okay, trim. Of course, there is no trim parameter for median. That wouldn't make any sense. And if you really think about that, why wouldn't there be a trim parameter, right? Because it actually just wouldn't make a difference. If we sort these lists and we trim one off from each end, we're still going to have the same exact median. That doesn't alter the median. Here we can look at this. The sample mean for urban, 21.5. Median for urban is 17. If we were to look at the trimmed mean for urban instead, why don't I do that? I think, what you might suspect, and we'll find out, the trimmed mean for urban happens to be the median for urban. Okay, so that's kind of an interesting indicator right there. There are scenarios where your mean and your median are equivalent, right? Or roughly equivalent, and that's an interesting thing to see, right? What might that tell you? It might tell you that values are fairly evenly distributed above and below the mean, if the mean and the median are similar. That's a good thing to notice in your data. If you notice that in your data, you want to talk about it. I'm not saying it means your data is better or anything like that, but it's a good thing to notice if your mean and your median are very similar. It makes it easier to describe certain properties of that data. So I'll go ahead and paste this in as it is. Yeah, exactly. The trimmed mean for urban is 17.0, which is in this case the median as well. And then I think that's an interesting indicator, right? That possibly, and we can't make a conclusion about this, but possibly that 80 is in fact an outlier, right? Could be, given what we're seeing as the median. What does that similarity mean? Well, with the trimmed mean, if we get rid of the highest and lowest values, then what we're doing is we are sort of creating a similar spacing of values above the mean as there are below the mean. And if we think about that, that might be a good indicator that that is a more representative state of our data, and that if we have this, this value 80 up there, that, that may be a little bit, sort of aberrant, right? Like it might be just way off on the right, a little bit too far. We have to make good decisions around that sort of thing. We have to actually be critical in regards to the phenomenon we're observing. Like the example I used before was, maybe in this city, there are places, one out of every 15 places perhaps, where that are in close enough proximity to, like a smelting factory, something like that, where, maybe these toxin levels are really high. And so if we eliminate the 80 because it comes up maybe once every time we sample, that would be doing a disservice to the representation of the phenomenon, right? We would want to take that into account. We wouldn't want to throw that value away in that instance. If there happens to be an urban house that, I don't know, somebody specifically was, I can't remember exactly what an endotoxin is, but somebody was cultivating an endotoxin in their house, for fun or profit, and we happen to measure that house, that would be an outlier, right? That's like, it's like some, for example, if we were looking at lead paint concentrations or something like that, and we just happen to sample a house where there's just an extreme lead paint enthusiast, right? We'd probably want to throw that sample, that numeric sample away. Just to, we want to make sure that we're representative, but we can't, representative of the phenomenon, but we can't base that decision on the data that we're observing. We have to base it on the data in light of the phenomenon itself, which means that we have to use real-world critical thought. We can't just assume that that the data is telling us the whole story. We have to look outside the data. Can the statistical functions in Python statistics module be used? Absolutely. Yeah. We don't focus on those in this course for a very specific set of reasons. For example, in one of the technical interviews, we might have you write a standard deviation function. We don't want you to import that standard deviation function. We want to see you write it procedurally. So when we're going about this, there are going to be a lot of things here where we are going to, for example, with distributions functions, we're going to handwrite the PMF instead of calling out to a statistics library to do that. We're also going to code the phenomena that can underlie the PMF. So when we get to binomial, we'll create a series of samples, and a series of Bernoulli trials. We'll do that by hand in a couple of different ways. So that's to not only give a basis for the theory, it's much more about having you program more, right? To think procedurally, to solve problems in that way. But by all means, feel free to write, to use, SciPy or a different, stats models, whatever you want to use, in your everyday, right? For this course, we'll be hand coding things. Right, somebody could be growing botulism. Exactly, somebody is a botulism enthusiast, and so if we're measuring, endotoxin is botulism. I don't know this, but or maybe botulism is an endotoxin. Either way, right? If somebody's an enthusiast in that, we want to throw that away. I think a fair way to think about it. The list of data is more uniform without the outlier. Uniform, not necessarily. I think of the distribution of values, the spaces in the distribution of values, is fairly, that distribution is fairly uniform. Uniform is not the right word. Fairly symmetrical around the mean. So, let's say we have a big space and a little space and another, really big space. If we do the same thing below the mean, in terms of the distances between data points, then the mean and the median will line up. Whereas if if we do that a little bit differently, if we have like on the left of the median we have big space, big space, big space, and on the right we have little space, little space, little space, then our mean is going to get dragged to the left. So it'll be left of the median at that point. But at any rate, we'll continue forward. So we've talked about two metrics here, right? We've talked about the mean and the median, and I want to point out a third one. I want to point out a third one that, well, sorry, before we do that, what I'm essentially saying here, and this is actually a good opportunity to draw a picture. If we have values, right? If we have these values where, let's say, we're going to build this around 5, right? So 5, 7, 9, 1,000. And to the left of 5, we've got, I don't know, got 4, 2, 1, negative 10. So if we're thinking about this, 1, 2, 3, 4, 5, 6, 7, 8. I need one more value over here. So let's just do 11 as well. Okay, so we can see that the median is 5, and I'll represent it like this. I'll say median is 5. So our median is 5. What's our mean? Well, our mean is going to be dragged way over here, right? Our mean, and I'm going to represent this as x bar. Okay, x bar we often will use to represent a sample mean. I'll talk about that a little more in a second. Our x bar is going to be somewhere out here, right? Because of the balance of the spaces between these values, right? Really, it's just this space right here between 11 and 1,000. What does this mean? Well, we have to qualify what we mean by this, but there's this idea of an outlier, right? So we might think of 1,000 as an outlier, and again, we want to be careful because if 1,000 is meant to be in the data, we can't really call it an outlier. Outlier is a human designation that we have to where we have to use critical thought in order to determine if that is or is not an outlier. That said, if we're thinking about centrality in the data itself, obviously the median here is giving us something that is central in this visual sense, right? Where we've got things, evenly spread around 5 until we get to 1,000. Whereas that 1,000 is dragging our mean to the right. And so what we tend to say is median is, the word we use here is resistant to outliers, right? The median is resistant to outliers. Something to remember. And when we get into measures of spread, we're mostly going to think about measures of spread in terms of the mean. But there are actually, how things are spread out around the center of the data is how we think about measures of spread. But there are median-based measures of spread, and we're going to look at one of those. That'll be the 5-number summary, IQR, and whatnot. Okay, so keep this in mind. Median is resistant to outliers. So let's move toward something a little bit different in terms of representation or centrality. What if we have a group of people, let's say, and that group of people has a set of skills, a set of interests. And I'm going to write down some interests here. Maybe person 1 likes, I don't know, cats. You'll probably hear me talk a lot about cats. Not Cats the musical, just to be very clear. So cats, I don't know, skateboarding, and I don't know, music. Music's a very generic interest, but let's just say. And then person 2, well, they also like music. And we're sampling 3 from each of these people. So music, and they like, I don't know. I've never done this, but I assume people like kayaking. It looks fun. And I don't know, darts. You know, I'm just trying to come up with something. And then another person likes music, and they happen to like darts. And they also like frogs, whatever. They like frogs. Okay, so if we're trying to think of commonality here, right? What's something that seems pretty common here? Well, obviously, if we're thinking about these interests as something like well, how do I say this? Like you know, this is a set of votes people are taking about things that people might want to do. Well, what is a representative interest in this case? It seems obvious that it's music. So we would call this the first mode. First mode is music. And then the other thing where there's commonality is darts. So we have a second mode called, which is the interest darts. So this is a fairly simple way of thinking about a representative measure. Except this isn't really a measure, is it? It's a thing. And you know, how would we order these in the world just arbitrarily? We can't really count these. We can't say that one of these is a higher value than the other. We can just say one is more frequently occurring. And you know, they're not numbers in this sense. So when we're looking at this, you know, music is obviously occurring more, and that's going to be our mode. The mode is very useful for, you know, things that we can't order, things that we don't number. It can be very useful also when we're looking at numbers where certain things occur more often than others. Like we can have a modal value when selecting from, let's say, a distribution of numbers, and that's fine as well. So this isn't really the center of a data set the way that the median is, or you know, to some degree the mean is or can be. It's just the element or elements that have the greatest frequency. So with that in mind, I'm going to have you write a mode function. And I want to give you, well, maybe I'll just use this. Yeah. Try. There's that. Cats, skateboarding, music, and then it was music, kayaking, and darts, and then it was darts, music, and frogs, right? So this is these are our interests. Just to frame this question, I'm going to have you write a mode function really quick. And I'm just going to encourage you to write this function very simply. Return the most frequent item, but don't worry if there are two modes, or we call that bimodal. We can write a more robust function here, but that's not the purpose. This is more to demonstrate a very simple algorithm that it's good to know how to program offhand because it comes up in a lot of other spaces. So I'm going to have you code the mode function, and yeah, I'll put 5 minutes on for that, and go ahead and get started. All right, let's code this up. So we're just looking to gather. We're looking at going over this list and just pulling out what is the most occurring thing. And the reason I'm including this here is that it's a sort of common algorithm pattern, and other functions you write will sort of look like this. So the mode of a list, a little bit bigger. The first thing we're going to do is select a value, right, from that list. And we might as well start with the first value, which is just index 0. So we're going to take index 0, and we're going to say that this is the most frequent value. We're taking a guess, okay? And then we're going to update that guess based on what we look at. So we can look at every other item in this list, every other item in the list, starting at 1. Oh my gosh, VS Code. Okay. So for each item in the list, starting with index 1, right? So everything else from index 1 until the end is what this is saying. We're going to say if the count of that item is greater than the count of the most frequent item in that list. Then we can just update the most frequent, right? We can just say, okay, well, the most frequent is that item instead. And at the end of all this, we can just return the most frequent item. Let's call this, so we've got, let's print the mode of our interests. And it looks like that would be music. Now, what happens in this algorithm if, for example, darts occurs the same amount of time as music? Music is the only item that shows up. And if you think about why that is, it's that we're using greater than here. If I change this to greater than or equal to, then this last occurrence of darts is going to overwrite the most frequent, and it'll become darts. Now, this is a very simple mode function. You can obviously make this much more complex. This is a deeper concept than this, but mostly I want to share this pattern, right? This is a type of pattern that comes up a lot. And you want to be able to take guesses and update those guesses with new observations. Okay. All right. So those are the three measures of centrality that we're going to consider. We're going to utilize these, going forward. We'll talk about median in light of measures of spread. We'll talk about mean in light of measures of spread, and we'll talk about mode in terms of most frequently occurring values when we get into distributions specifically. So that said, why did I start list at list sub 1? Because we already know list sub 0. We already collected it into that most frequent, and we can skip it. We don't have to skip it. We could just look at everything in the list, but there are times where there are situations that might necessitate you skip the thing that you already have, if that makes sense. So I just wanted to include it in there because it's a good example of slicing, right? It's like, well, we already have this as the first guess. We don't need to look at it. We don't need to compare our first guess with itself. We can just skip that one. Okay. So we're going to talk a little bit about sampling, okay? So there's this idea of sampling. And to talk about this, we need to understand a couple terms. There's a population from which we can take a sample. The way that I like to visualize this is, let's say we have a pool of every instance of something, right? Got this pool of stuff. And we want to sample from it in a way that ends up being representative of the pool. So maybe we take a little bit from here, and we take a little bit of here, 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 and here, and here, and here. And our assumption, if we do this sampling in a good way, in a reasonable way given the phenomenon, our sample should, when we take the mean or the median of the sample or other metrics, those statistics that we gather, right? The mean is a statistic of a sample. Those statistics should approach the population. Turns out we actually use different symbols when we talk sample versus population. Okay, so just get a different color here and say, when we're talking about samples, we think about these differently from when we talk about populations, right? So for the mean, a sample is represented with the symbol x bar. For a population, we represent that with this weird symbol. It's like a U with the tail on the front. That's called mu, okay? So why do we use different things here? Part of this is that we are almost always thinking in terms of samples. We're almost always thinking in terms of some selection from a population. And when we talk about samples, we actually call these things, the mean here would be a sample statistic, right? In contrast with a population parameter. And part of this statistic, a statistic is something that's flexible. It's related to a set of observations. We don't know everything. But what we're trying to do in general, and this isn't always what we're trying to do, in general, we're trying to make x bar look like mu. We want our mean to look like mu, our sample mean to look like our population mean. That's what we generally want to do. We also want our samples to be representative. In general, we want our samples to be representative. So when we talk about these statistics, often we're going to use a Latin-based letter, right? Latinic-based letter for the sample statistic, right? Here we've got x bar, x being the letter in our alphabet, and we're using a Greek letter to represent the population parameter. That's kind of in statistics. That's a tradition. So if you see something in the form of a Greek letter, it's likely a parameter and not a statistic. Okay, so it's in light of the population or the theoretical population. Okay, so let's think about sampling. Well, let's do a procedural tour of sampling. Great question. Is sample mean x bar capitalized X or lowercase x? It can be uppercase. It can be capitalized. In general, it's going to be lowercase x bar. I wrote that a little bit big, but that's a lowercase x bar. But it can be uppercase x bar. We see that too, either way. Okay, so approaching the population. What we'll do here, we'll actually approach a population. So we're going to take a sampling approach, and we're going to perform this in a way to try to approach a population parameter. Okay? So the way that I'm going to go about doing this, I'm actually going to import a function from random called choice. And what choice is going to do is, if we call choice on a list, it's going to give us one of the elements of that list. So I'm going to write a function here called getSamples, and we're going to have a range and a number of samples to get, right? So the number of samples here will be 5 by default, and we can change that. I'm doing that so that we can change it around. So I'm going to collect num samples into this this list called samples, and I can say for whatever in range num samples. When you hear me say that, for whatever in range, the whatever is this underscore. Okay, we don't care about this number. We don't care about 0, 1, 2, 3, 4 if we're calling this 5 times. We don't care about it. So we're using an underscore. We're not giving it a name. Purposefully not giving it a name. It's a disposable variable because the index here is not relevant. And I can say for every time here, we can say samples.append. We're going to make a choice from that sample range, like so, and then we can just return samples. Okay. So let's call this, and I'm going to kind of vary this a bit as we go. So the number of samples that we're going to start with is going to be 5. That's our default, but keep in mind that we can change that around. And I'm going to make a sample range that is all numbers between 0 and 99. Notice here I'm saying 99 plus 1, right? Because range is exclusive of the high value. I tend to write it like this instead of 0 to 100 because this very clearly is communicating to the reader we want to include 99, and 100 is going to be excluded. Okay, so what we can do, we can print the population parameter, which is mu, right? This is just going to be the mean of that sample range. Okay? Oops. There we go. Let's see what that is. The mean of the sample range between 0 and 99 inclusive is 49.5. Okay? So 49.5 is our population parameter. Now, we've got this sampling function up here, which is going to return some samples, and we're going to, build that those samples from the same range as our population. So we're kind of selecting from the same pool. If I do, I'll make a list called means. We're going to collect the means of our samples. I'm going to sample 100 times. No, let's sample 10 times, okay? And I'm going to say means.append. The mean of that get samples, passing in the sample range, and we'll start with the number of samples at 5 as I put above here. Maybe I'll make this a little smaller, try to fit it all in one, or most of it in one space, so you can navigate that, get a sense of what's going on. Okay. So what we can do is we can take the mean of these means, all right? And that's just the mean of means. And I'll put that in an F string as well, I might as well, right? This is the mean of means, and we can compare these. Remember, we're sampling 10 times from 5 samples, so 10 trials of 5 samples from which we're getting the mean. So, probably need to print something here. Okay, so our mu is 49.5, and our essentially something like x bar, I'm calling it the mean of means here, right, because the initial mean, well, why don't we take a look at this? I think this is a helpful way to think about this. Let's put an empty space here, and let's call this f string, we'll put in here, this is our list of x bar, and we'll just put in here the means, right? So let's take a look at what that looks like. Here's our list of x bars. Notice that these are kind of all over the place, right? if we only took 2 samples from this 0 to 99 range, change num samples to 2, and we're going to see something, 52, 29.5, 83, 17, right? These are kind of all over the place. And then we're taking the mean of that, and that's getting us not that far away from our mu of 49.5. We know the underlying phenomenon, right? We know what mu is here. We know what it should be. Now, how would we go about trying to make our mean of means look more like mu? How would we do that? Turns out it's not that hard to do, and this is one of those things in statistics and data science people are going to say all the time: get more samples, get more data, right? So instead of doing this 10 times, instead of collecting 10 values, let's collect 100 values, and instead of taking 2 samples, let's take 100 samples, okay? And let's see what we get if we do that, right? So we know that it should be, quote unquote, should be 49.5. Here, we're getting 49.5498. That is really close. And you might be wondering, well, how many times do we need to, or how many times do we need to sample from this to get 49.5 exactly? Well, 49.45. Okay, let's do 10,000 trials of those samples. 49.509, right? Like, the more we do this, we should be approaching, right? When I'm saying making our statistic approach the population parameter, this is what I mean. This is going to take a little bit, right? Because we're performing more and more loops as we go. But now we're pretty close. 49.498 is pretty close to 49.5. Are we ever going to get 49.5? Only if we do enough trials or a high enough number of samples that we essentially, our computer gives up on trying to be precise enough and rounds it to 49.5. That's the situation where we get 49.5 on a computer. And something that stands to reason here is that a sampling approach will never get you the population parameter, right? You can only get closer and closer to the population parameter if that's what you're trying to do. To be clear, that's not always what you're trying to do. But you always want your statistic to look as close to the population parameter as possible. Pretty much, you always want that, except in some sort of extreme experimental case where you're trying to do something fundamentally different. So I'll paste that code in. Encourage you to play around with it. We're going to be thinking about sampling approaches, and counting approaches is something else that we'll be thinking about at some point. But I'm mainly introducing this here to seed an idea. So last thing for today. Sorry, I'm not going to paste this input because it is a massive wall of input, right? That is too many to put in. But feel free to run it on your own. I pasted the code. Didn't I? Yeah. So the code is pasted in. The output here I'm gonna forgo because it's gonna take up too much space. Okay, so the last thing for today, in the last couple minutes we have here, there are a couple words that we want you to be familiar with. There's continuous data, okay, or continuous numerical values, and there are discrete numerical values, okay. The simple explanation here is that continuous values are measurements, right? Height of a tree in a forest we're going to think about that as a continuous value. But to really think of it as being purely continuous, we have to assume something I'm going to call infinite precision. Infinite precision just means, let's say we have some measure, right? This is some measurement between 0 and 1. If we zoom in on this, right, and we look at another measurement with finer precision, with sort of like microscoping in, maybe this is 0.3, 0.4. If we can do this infinitely many times, so maybe this is 0.3, 35 to 0.36. If we can keep doing this, what you'll imagine is that this, the number of decimal places here is going to be able to go infinitely to the right. That would make it purely continuous, okay? Time, we think of time as being continuous, time being a measure of entropy, in one of the definitions of time. But we can think about any instrument that has infinite precision as measuring something that is purely continuous. Continuous for us is going to mean that. And I want you to associate that with measurement. The thing I want you to associate discrete with is counting. And for the moment, we can just think about this as whole numbers, right? If I can count, 1, 2, 3, 4, 5. These are all discrete values because we're assuming there's nothing in between 1 and 2 if we're counting. If we're counting people in a room, we're not going to have 1.7 people. That's not how we're measuring that. We're going to be 1, 2, 3, 4, 5 people. So we're going to think about that as being discrete. Just to be clear, these don't have to be whole numbers. They just have to be able to be discretized in the sense of they need to be able to be separated from each other with an idea that there's not a value in between them. So I'm going to leave that there. And that's actually the last slide for today. So thanks so much for lecture today. We finished exactly on time.